State space modeling. By the end of this section, you should be able to understand the benefits and the drawbacks of using a state space model interpretation versus a transfer function model interpretation of a mechanical system. And you should know when it's appropriate to use one model over the other. You will be able to create state space models for linear mechanical systems, and in this model be able to identify the state vector, the input vector, and the matrices that fully make the system and the state space model. And we'll be doing this for single input and multi-input systems, as well as single output and multi-output systems. Once we are able to create our state space model, we will then numerically solve them in MATLAB, typically using ODE 4.5. And we'll see the relationship between the state space model and the transfer function model, and how we can go back and forth between the two for systems, both algebraically and using MATLAB. So first, we want to look at what is a state space model. Well, in general, the state space model is a way of representing the ordinary differential equations that make up our dynamic system. And really, that's what we were doing with the transfer function as well. In the transfer function, we were going into the Laplace frequency domain, and we were getting a representation between one output and one input in our system in the frequency domain. The state space model is an alternate way to represent these ODEs in a system. And one major difference we're going to see is that with a state space model, we are going to remain in the time domain the entire time. There is no Laplace transform. Everything stays with respect to the time t. And one use for this alternate modeling approach is that it is better for certain types of systems than transfer function, or at least it's easier to do some analyses. So for example, once we have multiple inputs in the system, the state space model tends to be a superior way to represent the system. And occasionally, when we have multiple outputs, the state space model would also be a preferred way to represent our system. One condition we used when using transfer functions is that our initial conditions were all zero. Our system began at equilibrium, and we were looking at perturbations from that equilibrium point. When we are solving our state space model, we are able to look at systems that have non-zero initial conditions and analyze their behaviors much easier than doing that with transfer functions. And this is good for systems that have what I'll call complicated inputs. So something more than just a step input, an impulse, a simple sine wave. If we have a more complicated input function, a state space model might be easier to use to, again, analyze the behavior of the system. When we were dealing with transfer functions, we were doing Laplace transforms. So if we have an input that it is not easy to take the Laplace transform of, then it might be not as easy to use in a transfer function method of modeling the system. Whereas with state space, we're seeing when we solve these systems that when we can do it numerically, the complication of the input is not going to be a major concern. And along with solving these systems, state space models generally have good numerical methods available, especially for the types of systems that we are going to look at, namely linear systems. But also they're going to be good with nonlinear systems, as we're going to see later in the semester. And really, in the background, when we are asking MATLAB to do the impulse or the step function on transfer functions, it is going to be doing the same numerical methods that we are going to be using when we have a state space model going forward. And with the state space model, we can use it to analyze the system for its stability properties. We're going to see in the next unit, when we actually start doing analysis of our systems using these models that we are creating, that both transfer functions and state space models are going to have this property. But the matrix form we're going to put this in, the eigenvalues, eigenvectors of these matrices are going to give us information about the stability of the system. Is it stable or unstable? Is it going to be asymptotically stable? And information like that. And state space models are going to be superior when we are looking at nonlinear systems, as we're going to be able to put any system into a state space form. Just we're going to have a different approach for the linear systems that we are going to concentrate on versus later when we have nonlinear systems. So these are some advantages or reason to use a state space model versus a transfer function. But what does the state space model actually look like? What are we trying to do? Well, we are going to take our ordinary differential equation or a set of ordinary differential equations, and basically we rewrite them first as a collection of first-order ordinary differential equations. As we've seen in the mechanical systems, the electrical, the fluid systems, and many other systems, we are often creating ODEs that are second order or potentially higher. And if it has multiple degrees of freedom in it, we're going to have a set of second order ODEs that we are going to be working with. The downside of second order ODEs and higher order ODEs is that they are difficult to solve, either for us to do by hand or for the computer to do. But the computer, at least, is going to be really good at solving first-order ODEs, and it would rather solve a set of first-order ODEs rather than even one second-order ODE, as we'll see later in this section. So we are going to rewrite the collection of ordinary differential equations that represents our system as this collection of first-order ODEs, and we're going to write it in this specific form. That we are going to have to create a state vector, x, which is going to describe really the degrees of freedom of our system. So the states are going to be the collection of coordinates that will completely describe our system, and this state vector is not necessarily unique. There might be different ways we can represent the states of our system, but it's going to be the independent degrees of freedom that represent the system. We are going to have an input vector u that is going to be the collection of all of the inputs acting on the system. As I alluded to earlier, the state space model is potentially better than a transfer function if we have a system that has multiple inputs acting on it. Thus far, we've only seen systems that have single inputs acting upon them. We're going to define this vector y as our output vector, or sometimes called the observables of the system. And now we're going to think about a little bit, what are we actually able to measure or sense in our system? That is what y is going to represent. As we go into the third unit and talk about control in the system, one thing needed for control is going to be observability. Eventually, we are going to want a very specific output of the system, so perhaps the position of the system we want to prescribe. In order to know if we've achieved the desired position, we're going to need a way of sensing what that position is so that we're going to be able to exert control. So we'll get into more about how does y come about in Unit 3. And we're going to be developing form matrices for the state space form. An A matrix that is going to multiply our state vector, and that is going to be called the state matrix. And A is basically a description of how the system is physically put together. In the case of mechanical systems, it's going to take into account all the springs, the masses, the dampers of the system, and the physics of how they're put together. We're going to have a B matrix called the input matrix, and that is going to describe how the inputs are interacting with our degrees of freedom. And then for the y equation, the observability equation, we're going to have a matrix C called the output matrix. And that is basically going to describe how are the sensors in the system put together? What are the degrees of freedom that we are able to measure using some sort of device? And then we're going to have D, a feed-through matrix. And that is going to represent how the inputs are actually going to interact with the sensors that we have in our system. Now, in this introductory course, we're going to see that the C matrix is generally just going to be made ones and zeros. We're going to act as though the sensors we have are going to be able to measure directly the states that we have in our system. And typically, we're going to see that the D matrix is going to be a zeros matrix, and we are going to treat the sensors as being independent of any inputs. But we'll talk about those interactions a little bit later, and as you take more advanced classes, you're going to see that the C matrix and the D matrix are going to get more complex than the types of matrices we will see in this course. So these equations highlighted here are the goal of what we want to create when we can say we're done with the modeling step. We have our state space model. We need to define X and U, we need to define Y from the prompt, and then we need to fill in the matrices A, B, C, and D. So all of this together is the state space form of our model. So at the onset, it does look certainly more complicated than what we saw for the transfer function, where we were just getting one equation, maybe two equations, and we called that the model. This is a lot more moving pieces to put this whole model together. So how do we go about finding all of these different items that we need in order to put together our state space model? Well, we're going to have some general steps when we're modeling specifically here mechanical systems, but we can generalize this out to non-mechanical systems as well. So the first step when we have our mechanical system, well, we're going to need all the necessary free body diagrams. Every mass that is able to translate or rotate is going to need a free body diagram, and if we have any nodes in the system, we need the free body diagrams for those as well. We're going to take these free body diagrams, and for each of them, we are going to write an equation of motion, possibly multiple equations of motion for each free body diagram if there are multiple degrees of freedom possible for the different masses or nodes or objects that have inertia. And we're going to write this equation of motion in the time domain. At this step, at the end of step 2, drawing the free body diagrams, writing out our equations of motion, this is the same first steps that we took when we wanted to take the transfer function approach to modeling our system. So at the end of this point where we have all of the equations of motion of our system, now we can make the decision, do we want to take a transfer function approach or a state space model approach? So for the rest of this, this is where we kind of branch out, and the steps we take from here on out are different than when we wanted a transfer function. So in a transfer function, we would take these, we would take them into the frequency domain. We're not doing that here. What we're going to do is look at the collection of equations of motion that we wrote. And we are going to identify the inputs and the states of the system. And from the inputs, we're going to create the input vector. And from the states, we are going to create the state vector. Now, how do we determine what's an input and what's a state? Well, starting with the input, anything that is prescribed in the system, so for example, a prescribed force or forces acting on the system, or a prescribed displacement in the system, that would go into the input vector. So similarly, when we decided what the inputs were when looking at transfer functions, that's what we're doing here. But potentially, we're going to start to see multiple inputs into the system and not just one. Then we need to identify our states in order to put those in the state vector. This is a little bit more complicated than what we saw for transfer functions, where really we were counting up how many outputs our system had. In the transfer function method, because we were taking a Laplace transform, we didn't see any derivatives of output variables because a derivative just became an s or an s squared times one of our variables. But because we are staying in the time domain, we are now going to be seeing zero derivatives, first derivatives, and second derivatives of dependent variables in our system. So when we are identifying state variables for a state space model, we want to look at every output variable or every dependent variable that is not an input, and all but its highest derivative is going to be a state variable. Oftentimes, the highest derivative we are going to see on an output is a second derivative, meaning that its zeroth derivative and its first derivative would be state variables. But we want to be careful of this because there will be times where the highest derivative in any of the equations of motion is only a first derivative, or potentially we could see a third derivative. So the general rule is all but the highest derivative in any of our equations of motion become state variables and go into our state vector. So we're going to see in the examples really how we are identifying these different variables and putting them together. Once we've established our input vector and our state vector, which means we've identified our input variables and our state variables, we want to take the equations of motion that we wrote previously and rewrite them in terms of state variables and input variables. And the hope is that in any of these equations, we are now only going to see a first derivative term in any equation. A rule that we want to go by is there might be several state variables that we could put in for one of our original variables. And the rule we want to follow is that if a variable can be replaced by a state variable rather than the derivative of a state variable, it must be. So at this point, we have our equations of motion rewritten in terms of our state variables. And if it's a more simple system, each equation will have only a first derivative term, no second derivatives. And it will have only one such first derivative term. At this point, we want to take our equations of motion and isolate the first derivative term on the left-hand side, and then put everything else on the right-hand side. And we want to group coefficients in front of state variables. We want to group coefficients in front of input variables. So now all we have is our equations of motion rewritten in terms of different variable names. But now we need to go on. Again, grouping those coefficients in front of the state variables and the input variables. Now we are likely going to need what I call mapping equations that are going to relate the derivatives of our state variables to other state variables. And this will become more clear in the examples why we're doing this and how we are doing this. But the point of step 6 is that by the end of it, adding these mapping equations, we will have as many equations as we have state variables between the equations of motion and these mapping equations. We're going to take all these equations and we are going to put them into matrix form. So this collection of equations is going to form the A matrix and the B matrix when we put together our state space model. So once again, the A matrix, the B matrix are relying just on how the system is put together. So we're going to be able to write that x dot equals ax plus bu by the end of this step. Now, we still need that other part of the equation, the y equals cx plus du part of the equation. So now we have to create the output matrix C and the feed-through matrix D. So we're going to know in the problem what are the outputs that we are trying to track. Is it positions, all of the positions, some of the positions? Is it velocities, some of the velocities, all of the velocities? For this course, that's going to be told to us. But in reality, these are going to be the different variables that we are able to track with our sensors. So we're going to keep it pretty simple for this course and say that we are tracking directly the different states using sensors that directly track, let's say, positions or velocities. So usually the C matrix will be made of only ones and zeros, but that's only going to be true in this course, not in general. And D, how the inputs interact with those sensors, is going to be, in this course, generally 0. We are going to have the simplest type of models where the inputs are not going to interfere or interact with the states that we are censoring. But C and D will get more complicated in follow-up courses to this. And these C and D matrices are going to be crucial when we are going to be talking about observability and controllability if we are trying to control systems when they are in the state space form. So again, we're not going to do that in this course, but in a follow-up controls course, the A, the B, the C, and the D matrices all come into play when designing controllers for state space modeled systems. When creating these A, B, C, and D matrices, we want to pay attention to not only what goes into them, the relationship between the state variables, what we're sensing, the interaction between our inputs and our state variables, but also we want to be very careful about the size because we are making a linear algebra matrix form of our ODEs. So the size is important because we want to be able to do matrix operations here. So let's say we have a system where we have identified n state variables, m input variables, and p outputs or observables in our system. So n, m, and p will always be an integer number. Before we are done with our model, we want to ensure that that A matrix, the state matrix, is n by n. So the number of state variables by the number of state variables. A is always going to be a square matrix. B, how the inputs interact with our physical system, will always be n by m. So n rows by m columns. The C, the observability matrix, will always be p by n, and the throughput matrix D will always be P by M. So again, we can identify how many state variables we have. That's the size of the X vector we create. How many inputs we have. That's the size of the U vector. And how many outputs or observables we have. That's the size of the Y vector. So we can get N, M, and P and ensure that all of the matrices are sized appropriately.